My name is Pathak and I'm a third year PhD student in the Department of Agriculture and Biological Engineering at Purdue University. The title of this presentation is Autonomous Navigation in Digital Agriculture using the segment annotation model for corn row identification. Now, the agricultural industry is facing shortage of skilled laborers for various tasks, such as scouting the field and requires automation. These tasks can be automated by deploying robots, which can precisely monitor the plant economics that combines the aspects of genomics, physiology, and navigating these robots in the agricultural field is challenging because of varying soil conditions and changing canopy structure. There are several methods that have been proposed in the literature for navigation of these robots, such as global navigation satellite system, which fails in adverse weather conditions and under dense canopy. While the light detection and ranging, often termed as LiDAR, fails due to dust and obstacles and is pretty costly, therefore cannot be used by farmers. On the other hand, machine vision based methods seems to be an effective solution because the cost of the device is not too high. Machine vision methods can be categorized into three types, out of which filtering and line-based methods are computationally expensive and lacks robustness, especially when the corn rows are off linear due to the elevation. While segmentation methods are easy to use, but using the same thresholds won't provide good results because of the changing light intensity, which you could see from the GIF file on your screen, that the light intensity changes a lot under the canopies. Therefore, using segmentation methods requires some special techniques to automate the value of the thresholds. So therefore, of this research is to deploy the segment annotation model for detecting the navigation path of robots. So if we talk about the materials and methods, the images were taken from the Intel Geoscience D455 stereo-based camera, which was placed around 25 centimeter above the ground level. And if we talk about the segment annotation model, so the general structure of the segment annotation model has image encoder, prompt encoder, and mask encoder. The task of the image encoder is to derive the feature impedance to the high resolution images, while the prompt encoder requires the prompts, and these prompts could be sparse as points or bounding boxes or dense as equal masks. The mask decoder employs the prompt self-attention and bidirectional cross-attention mechanisms, allowing it to effectively align images and prompt embeddings to produce the desired image masks. It is to be noted that the domain-specific prompts improves the performance of the segment annotation model. Therefore, we provided access gene identification index-based prompts, which is very commonly used in the field of agriculture. So once the masks were created, the number of pixels across each columns were calculated, and the column with the maximum number of pixels is decided as the path for the robot navigation, and the angle from the midpoint of the image to the corresponding pixel, which is being termed as the final direction for the robot navigation, is being calculated and termed as the angle for robot navigation. So to test the accuracy of the model, each image's endpoints were annotated by a different user so that the test data set is neither seen by me or by the algorithm, and the corresponding angles were also calculated. In this work, this was done by Dr. Yaguang, Zhang, who is one of the authors in this paper. And the difference of the angle from hand annotation in the algorithm provided is being used for testing the accuracy. So as del alpha tends to 0, the accuracy of the model improves. So if we talk about results, using the excess green segmentation index-based prompts provided better results than using the segment annotation model alone. The intersection over union, IOU, a pretty common metrics used to check the performance of models when using them for segmentation tasks, ranged between 55.2% to 98.9%, which is pretty high and acceptable in the agricultural domain. Difference between the hand-annotated and the algorithm provided angles del alpha ranged from minus 5.72 degree to 8.72 degree in most of the cases. Only around 8% of the images has these angle del alpha ranging from 19 degrees to 48 degrees. The root mean square error of the algorithm was around 9.78 degrees, which is kind of acceptable in the agricultural domain when deploying the models in the field scale. So limitations and directions for the future work. In the past slide, we have seen that around 8% of the images has del alpha values pretty high, which will be due to the fact of point clustering and leaf senescence, which affects the segmentation accuracy of the model. So to improve the accuracy, the model should be trained with a pretty diverse set of images. For off-linear rows, which was not targeted in this study, you only look once, YOLO, or other lightweight architecture should be deployed for getting the navigation path for the robots. Furthermore, these high values of del alpha is kind of acceptable if we use the finite state machines where we provide the conditions that if del alpha values are less than some particular threshold, then only it should consider the new values coming to it within each image frames. Else, if del alpha values is greater than the threshold, then it should consider the past values from the previous images. For conclusion, I would like to say providing prompts based on domain expertise improves the accuracy of the segmentation analytic model. Image segmentation significantly affects the accuracy of the navigation algorithm, and finite state machine can be deployed to overcome the anomalies in these angles. I would like to thank all the co-authors for their collaboration and guidance, both Center and Department of Ag and Biological Engineering for all the resources, and IIT for Ag for funding this. Thank you, and I'm open to questions.
You can take questions from your. Actually, you have Purdue. Yeah. A strong group, both in Purdue and UAE, working on this digital agriculture. Yeah. They were here, Questions from the audience?
So I'm just trying to understand, like, currently your architecture is that you are trying to identify the green pixels first. Then
We are identifying the soil first, not the green pixels.
you are identifying
The soil.
Five.
the soil.
Yeah, we are trying to eliminate based on the excess green index, all the vegetation that's there.
Yeah, I mean, forget that, but to go back to your methodology. Yeah. So your input itself is just excess green points as the prompts.
Yeah.
Nothing else, right?
Nothing.
And then you're making an assumption that the excess green are corresponding to the.
So we have the threshold for the excess green vegetation index. So if the excess green vegetation index is pretty high, then it's considered as the plants. And if it's pretty low, then it's considered as the background or the soil. So we are removing, like based on the thresholds, we are removing all the high values of excess green and then randomly selecting 3 points, which are given as the prompts for the segment anything model to train and like make the mask.
Okay. So why are you not taking a direct action? If your goal is to determine the soils, if you take the prompts corresponding to the soils.
So that's like the future work that we are doing. So not just with the excess green, now we are like trying to incorporate different types of vegetation indices and trying to see like which will be the better one. Because the thing is like the soil properties and colors could change
Okay,
as
I got
respect to.
And another question, what did you mention in the conclusion about the yellow items? So how will yellow?
So if we talk about like the states like North Dakota, uh, Iowa, those are like have the changes in the elevations and the rows are like not straight. It's like curvilinear. So if we deploy the segment anything model directly, then the thing is like, with this approach, it's like counting the number of pixels across each columns and like summing it and then giving the results. And when it's curvilinear, so the thing will be that pixel value, like the maximum number of pixel value will not sure, we are not sure like whether it will tell the direction of the row because it will be always telling the straight thing. So if we have like the YOLO, so rather than then focusing on the soil, we can start focusing on the plants and create the bounding boxes to train the robot based on the plants.
I see.
How about
Sorry?
fusing different types of data for different mechanics? Like if you take some microwave data,
So this work
optical
was,
data,
so this is a robot which is usually made for like phenomics kind of things. So they were, so due to the payload limitations and like the small sizes. So that's why we are going with the RGB. And for now, like outside the rows, like in the field, it's using the GNSS RTK, but when it comes with the field, then someone have to go and like navigate it. So we are trying to automate the entire process.
but which one would help you? Is it the road or the soil or the green or the thing?
I think for the straight rows, it will be the relative, like how it goes.
Okay, so just quick questions. So your task is to segment, you're using a SAM model, right? So you need to, you're detecting soil moisture area or what is that? Can you just elaborate?
We are trying to detect the soil spectral signatures
Yes.
based on the RGB.
Okay, okay. Did you plot it here somewhere? Says that no, no. Spectral signature, have you analyzed?
We analyzed it's in the paper. We didn't plot it on this.
It would be better if I like once la. Okay, fine, thank you.
Yeah, thank
Your paper is not accessible for us right now.
Uh, Thank you, Harsh. We'll move on to the next paper, paper number 75. The authors are Prakash, Pilinja, Subrahmanya, and Bharath Raj. The title is Investigating the Viability of Detecting Rooftop Solar Photovoltaics via Convolutional Neural Networks using Remote Sensing Images.
I'm very much for the university. How this new paper, it should provide the detecting local solar photovoltaics via convolutional neural networks using the more sensing images. Introduction. The International Energy Agency estimates that solar energy accounts for 3.6% of all the energy produced currently. And according to a report from TV magazine, EVs have become the cheapest source of electricity in many parts of the world. Make up for a large part of energy consumption, and there's a 3% electricity loss during transmission and distribution of electricity. So PVs for households can actively contribute to lowering these losses and moving towards the future of net zero emission. So considering this, it is useful to investigate the number of building routes that already have PVs installed to monitor and plan for future actions, right? So using remote sensing images from satellites or drones, it's possible to identify PVs that have already been installed in routes. And one approach to automating this process is using convolutional networks and training them with large amount of data, assessing them and checking how they perform. Evaluating these CNNs with real-world examples such as understand the viability of detecting these CNNs. Jumping into the literature review, currently literature, there is a lot of methods for solar panel detection using random forest, CNN-based segmentation. And there are also case studies that use, there's one case study that will give an architecture, a pre-trained model with BGG such coding. And there's also software tools that employ hybrid approaches that combine different machine learning models such as KVs, SVMs, and CNNs for final identification using imagery from like allocations, bunch allocations from Northern Lighting. And there's also a framework called the Solar Machine Learning Framework. Its socioeconomic characteristics with solar PV density and census tract level. There also is bunch of papers that describe data sets that have been prepared for this task, and there is actually a very less number of complete data sets for this use case, and we found two usable ones. One of them is a data set that uses aerial photographs from Beijing or Beijing spatial resolutions built for PV segmentation. Another one was a crowdsourced data set that was built by an initiative of a crowdsourcing initiative of our community has contributed towards labeling the satellite imageries that was obtained from Google. And we chose the imagery data set that the crowdsourced one because of its diversity in locations. It spanned a lot of different areas of locations, and it has 13,000 images, and each one was 400 into 400 pixels. So it was enough information and enough data. It was a large amount of data actually. The method that we planned was simple. So the 4 stages, we have to organize and pre-process data for, and we repurpose the data sets for semantic simulation into object detection, and we trained past in this exam in this situation with the repurposed data set, and we tested the data set with, we tested the model with the pre-partitioned test data set, and then we later validated it with real world examples to a manually prepared data set. Let your past opinion after going through a bunch of models and testing of models, and we decided that past opinion is better and more effective due to its quicker training period. So for past opinion, it's an object detection model, so we had to repurpose all of the masks into bounding boxes. We did that by extracting contours from each closed shape in the mask and created bounding box able to make the data format as Pascal walk, and we later split it into an 8:2 ratio. The method we chose was fine-tuning the big model instead of training from scratch, because fine-tuned models have knowledge. So that could be that could actually be very helpful in getting better results. Accelerated fast matching then due to the training, more effective use of computational resources. It's very robust. So the learning scheduler, we selected the learning rate to decrease 10 times every 3 epochs, and we fine-tuned it for 4 epochs with each epoch contained 1 or 8 iterations, and at which the training loss and even the metrics precision algorithms seem to reach convergence, and any more training will get to overfitting. So the initial metrics that we got after training for 4 epochs was 80% precision, 85% variability, which seems pretty promising. It seems like a very good model. This test was done with the pre-partitioned data set, which on which the data was trained. So the data tested is very similar to the training data. So that could account for good performance. But we only know better if we check with the other real world examples. For that, we manually constructed a data set which has 85 images from Google Earth that was between May 2022 to April 2023 that corresponds. And it was manually labeled by us with corresponding bounding boxes for 9 distinct cities: Bangalore, Beijing, Kyoto, London, Los Angeles, Mauritius, New Delhi, New York City, and Taipei City. So this data set offers a thorough evaluation of models' performance across various urban and suburban environments, including cities in various areas of the world. And the evaluation metrics for this are IOU, intersection, OU, precision, recall, and reference. So the results we got from this evaluation was very different from the previous evaluation, which was the test data set. And this metric showed that the average IOU is actually 61%. Even though the model, the bounding boxes are very precise, the recall seemed to be 67%. The low recall indicates that and low recall and low reference score and IOU indicates that the model is producing a lot of incorrect labels, so very difficult has a lot of patterns, which can be seen here. This is one example prediction where the model said detected some patterns very precisely, but it missed a few compared to the control. So looking at more examples, we've seen that it's like some of the examples. The first example is very accurate in its prediction. The second one also is very accurate, but it missed one solar panel that was present in the ground. Just me. So the initial metrics were moderately high, with new metrics for the more clear picture. And technically, any more training with this model would have led to overfitting. The data was diverse and large enough that we see that the the problem with this is actually accounted to the architecture or the model itself. The model is failing to generalize across different settings. According to what we found, the metrics were all unevenly distributed and it was inconsistent. So it appears that the past RCN is simply not robust enough to reach the practically applicable performance. Yeah. In brief, we looked into whether or not it's possible to use CNNs to detect rooftop solar panels from the emergency images. We fine-tuned the past RCN diverse and large data set and comprehensively evaluated within the minute repair data set. And we concluded that the architecture performs okay. I mean, it does detect solar panels. It is, but it's just it's just a little inconsistent, and it may not be usable for practically practical use cases. And in speculation, if you're allowed to speculate, we are larger, even larger results like using vision transformers or CNNs as combination in a more robust architecture may lead to more practically applicable results.
Questions from audience? Anyone want to ask anything? Any question? Yeah.
Understanding that this is an object, not an object segmentation.
Object, yes.
Why you did this segmentation?
So we were testing bunch of CNN models and we wanted to train FASTA CNN because of its training time. And it was basically for us, it was easier after testing bunch of models, it was easier for us to go with object detection. So basically we chose it and, because we did a comparative study between Google Deep Lab V3 which, and FASTA CNN unit. And based on the training time and how well it's performing, we basically if we want to practically have a panel detection system, it's okay for us to actually have boxes too. We just wanted to have a high level overview basically on how applicable CNNs are in this use case.
The data set, the labels are available to you both in the format of boxes and the pixel-based labels?
So pixel-wise, it was available, and basically converting them into boxes is a not problem.
Yeah, that's it. So it was originally pixel-based.
Yes.
Okay. So one thing I observed that if you can go the training part, right? Because this train model you are deploying for testing for on that Bangalore region, right?
No, Bangalore region, but bunch of other cities.
Okay, fine. But since you have just trained your model only for epoch, that would not be enough. So you need to go at least increase that. This is the curve is loss curve, right?
Yes.
Okay. You would just train little more epoch, right?
It reached when we were training it, it reached convergence, and later epochs actually increased the loss because of
Loss was increased.
yeah, and basically
So
IOU
you tried then YOLO
validation.
models. YOLO tried it, that would be better. Because this is okay as in the beginning, like when you started the concept, later on the retina data even introduced, and then it was also not so good. Then the quick researcher moved to the YOLO. So now currently YOLO V8 is there. So you can test with that model. Probably that will help you to get a better accuracy.
Bharath, you are a student?
Yes, BTech third year engineering.
No, so I think there is some unique shape, right, of these objects that you are trying to segment.
They're rectangle.
Huh? They're rectangle.
Yes.
Solar panel.
No, but why you don't try shape-based segmentation?
I feel like going shape based is purely we need so much more than just the geometrical information for because we're looking for a generalizable applicable for any circumstance
You
model.
mentioned that its results are inconsistent and you cannot generalize the model. And that is because the approach that you have chosen is not contrast induced, and you have to take some shape-based segmentation approach. There are geodesic active contours. Have you heard of it? Geodesic active contours. I think they will help you make those things very precise. But probably clubbing with your CNN.
Yes. For us, the study's goal was to just assess CNNs and how actually applicable they are.
Okay. Any more questions? Okay, thank you. Thank you,
We'll move to the next paper, paper 130. The authors are Pyare Lal Chauhan, Jayati Vijayvargiya, and Anand Kumar M. Ramya. You are Jayati.
Yes.
Yeah. Okay. The title is Addressing Class Imbalance Challenge in Semantic Segmentation of ALS Data through Performance Analysis of RandlaNet and PointNet++. 130, right?
Hey everyone, today more than 57% of the world's population is living in urban areas. Thus, understanding the urban scenes becomes very crucial for informed decision making, sustainable city development, effective governance, and planning. In regard to same, we here present our work on addressing the class imbalance challenge in semantic segmentation of airborne LiDAR data over urban landscape through the performance analysis of two prominent deep learning architectures, RenderNet and PointNet++. We are Pyare Lal Chauhan and Jayati Vijayvargiya, Anand Kumar M. Ramya student from Indian Institute of Space Science and Technology, Thiruvananthapuram, presenting our work in InGARSS 2023. Airborne LiDAR point cloud data provides precise 3D urban data and captures the terrain with high accuracy. It has potential applicability in the fields of 3D city modeling, utility mapping, transportation mapping, vegetation analysis, flood modeling, disaster response and recovery, and many more. But the point cloud data comes with its own challenges. The point cloud data represented by XYZ, other attributes, and class is an unstructured data which is irregular, and also over a large terrain it becomes very, very voluminous. Thus, the data comes with its computational complexity and its classification accuracy hinders due to the class imbalance challenge. In this domain of semantic segmentation, many people have worked previously. They have utilized the handcrafted geometric or spatial distribution features on machine learning approaches for point-based and object-based classification. And in the recent times, deep learning approaches of point-based or projection-based are very prominent. PointNet++, and the convolution-based architectures like PointCNN, Tangent Point, Sparse PointNet, and others are being generated every day. But the large-scale point cloud data comes with its own complexities. It has been observed that many of these approaches that we have seen are demonstrated on a smaller or a localized dataset or the synthetic datasets like KP. The computational complexity when we deal with large-scale point cloud data is tremendous. And also the algorithm efficiency should depend on the feature extraction, the association of features, and the pattern in which the deep learning architecture is constructed for its efficient classification. In this regard, the class imbalance becomes a very, very prominent challenge. For this work, we have utilized the benchmark dataset DAILS, that is Dated Unlimited LiDAR Earth Scan, which is spread over the city of Surrey, British Columbia, Canada, over an aerial extent of 10 square kilometers, having more than 5 billion points distributed over 8 classes, namely ground, vegetation, cars, trucks, power line, poles, fences, and buildings. In this data set, a few of the classes like buildings, ground, and vegetation are significantly represented, whereas the other classes like poles, truck, power line, fences, and cars are not that significantly represented, as we can see in this figure. In this regard, our work is to manage the class imbalance challenge and see the performance of the two deep learning architectures, PointNet++ and PlinjaNet, for particularly means and minor class extraction in the real world urban LiDAR dataset over the city of Surrey, British Columbia. In this experimental implementation, we have utilized the dataset, trained in the test dataset, and have implemented the same reprocessing steps for giving in the two deep learning architectures. The dataset was divided into big blocks of 5 meter by 5 meter for further processing. PointNet++ stands out as a powerful deep learning architecture tailored for the intricate tasks of processing and comprehending 3D point clouds. It is built upon its predecessor PointNet and introduces hierarchical neural network architecture, which employs set abstraction and feature propagation layers. The set abstraction layer enables the model to process the points at various scale, progressively grouping the points and extracting features and aggregating them for comprehensive representation. The feature propagation ensures the layer for seamless information flow across different scales, refining the global features with global context for a more robust representation. Point++ operates directly on the raw point cloud data, capturing their intricate geometric details while maintaining the invariance to point order permutation. In this implementation, we have used a minimum size of 8 and an initial point cloud set of 8192 per distribution of 5 meter cross 5 meter and have used training epochs 50 with atom optimizer and cross entropy as a loss. The class imbalance challenge comes because in most of these approaches, for example, as we have seen in pointnet clusters, the data is divided into samples and blocks of a spatial context. Thus, the geometry of the object, which is a key parameter for semantic segmentation, gets distributed. And with objects, for example, power line, poles, and fences, which are not that majorly represented, lose their geometry. It offers a solution to this limitation of processing large-scale point cloud data by significantly downsampling the data. The architecture involves 3 major steps: local spatial encoding, attentive pooling, and directed residual block. These steps are implemented concurrently on each 3D point, comprising local spatial encoding, attentive pooling, and directed residual block, which collectively retains the relative position of neighboring points and replicate features. The local spatial encoding specifically captures the local geometric patterns, leveraging the spatial coordinates for spatial awareness, attentive pooling, and the attention mechanism, and learns the emphasis feature in local neighborhood, addressing this challenge of information loss in random sampling. The efficiency of this approach lies in the crucial role played by random point sampling for computational efficiency reduction. The architecture adopts the encoder-decoder structure with skip connections encompassing 4 encoding-decoding layers and 3 fully connected layers followed by dropout and prediction layers. To ensure the efficient feature extraction, a downsampling ratio of 4 was set at each layer. The training parameters involved 100 epochs and a batch size of 8 with a learning rate of 0.001, contributing to the overall effectiveness of RenDaNet in semantic segmentation tasks with the given dataset. Fusion of 2 prominent deep learning architectures, pointnet++ and RenDaNet used in this work is shown here, and it is very evident that for both major and minor classes, RenDaNet has outperformed. The mean IOU of RenDaNet is 0.61 as compared to 0.48 of pointnet++, and it is attributed to the spatial local feature aggregation module of RenDaNet that it captures the geometry of the object. The major classes ground vegetation and buildings, the accuracy prediction has increased by 1 to 3%, whereas for the minor classes, the accuracy prediction has increased significantly by 13 to 48%. RenDaNet excels in predicting all the minor classes except power lines. And in conclusion, we can say that the findings underscore the efficacy of RenDaNet and suggesting for its future advancements in the field of real-world large-scale point cloud semantic segmentation. And there is also future scope for utilizing the emerging approaches like attention transformer, adversarial network with focus on capturing and retaining the geometry of objects. As in this work, it is very evident that geometry contributes to the semantic segmentation accuracy of both major and minor classes. Thank you.
Namaste everyone, good afternoon. This work was a part of the major work I'm doing, that is building 4D digital twin for urban governance. So in 4D digital twin, buildings is one object which is majorly taken into the picture. But when we talk about urban governance, other objects like poles and power lines become very, very dominant. So that was the motivation of this work. The future of this work, which was not there in the paper, so I did not present it, is most of the recent papers you see that which are using pointnet as an architecture and then applying it on the machine learning networks. Okay. But in this way, we got to learn that the interpooling and the feature aggregation module used by RenDaNet is more effective in extracting the relevant classes. So in the predecessor, in the next work, what we have used is we have used the RenDaNet feature aggregation and the other models, and then applied the relevant machine learning model XGBoost to improve the performance. So this was a middle chunk of the paper. So I'm open to any questions.
From audience, questions from audience? Okay, sir.
Any digital twin you develop?
Yes, sir, digital twin, we have already developed that is with buildings. The major challenge,
Specific city.
for Trivandrum, for a area of Trivandrum of 9 square kilometer, we have, for Dales, we have, that is using buildings only. But when we do for urban governance and building 4D digital twin, so that digital twin will firstly have all the objects, and secondly, we have other thematic information as well. Like power line poles, everything has to be in the 3D. And along with that, another information. Suppose if some land use zoning is done or flood mapping is there, then the 4th dimension will also be added.
Are using the laser scanning camera.
Yes. So we have required a region of 100 square kilometer over the area of Trivandrum from airborne LiDAR scanning. So the major challenge is to detect poles, because what happens in India is not a planned urbanization.
You mean the electric pole?
Electric poles. Electric poles and power lines. In power lines, we are not able to do it because it's all covered in the trees, but poles is what we are doing. Because it becomes very, very important for asset management, which is one of the applications.
Now many cities are going for underground electric cables like that.
Yes, sir. Yes, sir. Many cities are going, but they are going. Like in the 4D digital twin model which I'm developing, that is sustainable because we can add more things to it. But before adding more things, we should know where are the things existing. Yes. So this if we can, because we don't have a very accurate training set for the Trivandrum. So we have also tried transfer learning and other things like that. But from this paper, what we got back is Rendland architecture can be very effectively used with XGBoost. And and for some classes, I'm using Rendland architecture. For some, I'm deriving simple features. Like for power line, I'm deriving simple features. With that, I'm able to get accuracy of 97% for power lines. And when I'm using XGBoost with our poles, I'm able to get accuracy of 80%, 82% for poles. So with 82%, if I'm able to get poles, that is good enough. Buildings, if like out of 1,000 points, if I'm not able to detect 10 points, is okay, because still the building will be there. But if for poles, if I'm able to detect, that is not relevant for my application.
Just two questions. Since your task was addressing the class imbalance problem, so since you have used the critical cross entropy, so you would opted maybe tried some other loss function which mitigate the problem of the class imbalance.
Yes, sir. Actually, heuristically, we tried a lot of approaches, being very true. And this was the best we could get, like even for the neighbors, like best increase in the accuracy for small classes. But yes, we can actually try.
Tried some other loss, for example.
No, loss we have not.
Because
we tried instead of KNN, we tried that spherical bounds. So I tried that neighborhood.
Weighted critical cross entropy would be more options, or maybe going higher loss, advanced loss.
Yes, sir.
Focal loss, Tversky loss, or maybe.
I will take this into consideration for another. Yes.
What is the other drawback of that we call
point
problem? This Rendland model.
Rendland drawback.
Rendland is giving better, right?
Yes, Rendland is giving better.
But what are their other? I mean, their problems, drawbacks of that model.
Okay. What I find like Rendland is able to aggregate features very properly, but at the encoder-decoder level is where the classification confusion comes.
So among two, which one is more complex model?
More, of course, Rendland is more complex. A lot of steps are there in that. PointNet plus, I cannot comment. Like while programming.
Next time as a like a study part, so to keep in mind the computational complexity as well.
Yes. Computational complexity of Rendland is in our processing, Rendland became more computationally complex. Although they say that they don't take more memory according to their paper, but this memory issue and all we face more in while working with Rendland.
Should be reported as
yes.
Okay, fine. Thank you.
Thank you very much.
Thank you. We'll move to the next paper. We are running a little late now. So the next paper is paper number 197. Our authors are Naveen Chandra and Himadri Vaidya. I believe we have Naveen online.
Yes, I am online.
Yeah. So the paper title is Attention-Based YOLO V5 Model for Enhancing Landslide Detection in Remote Sensing Imagery.
A very much from the Institute of Himalayan Geology, Dehradun. The topic of my presentation is attention-based Viability model for enhancing landslide detection in remote sensing imagery. Landslides are the serious hazards which are generally unexpected. The causes of landslides includes the heavy rainfall, earthquakes, snowmelt, and anthropogenic activities. Landslides affect human life, infrastructure, as well as the economy across the globe. More landslides are anticipated due to the present weather and climatic conditions. Therefore, the timely prediction and accurate detection of landslide is very crucial. The traditional methods of landslides includes the field investigation. However, with the advancement in remote sensing technologies, the availability of high-resolution satellite images can be utilized in the studies of landslide. The remote sensing-based methods includes the visual analysis, pixel-based as well as object-based, and artificial intelligence and machine learning-based approaches. The progress in the computational environment, that is the GPUs, the accuracy in terms of landslide detection is expected to be improved. In the past, the various automated and semi-automated methods have been developed by the researchers. However, the machine learning and deep learning approaches have outperformed these other conventional approaches. Therefore, the objective of this study is the application of attention-based Euro-V5 model for landslide detection. Particularly, we applied two attention-based models, that is the CBAM and ECA. We conducted the experiment using the satellite images and we compared the results of both the models. The dataset utilized was the open source dataset, that is the BG landslide detection database. It contains 2,775 images which were acquired from the triple set dataset with the resolution of 0.8 meter, and the ground truth of the database is available in the form of binary masks. This is the overall methodology. It includes the data collection, data pre-processing, data preparation, training the deep learning model, validation, and the application analysis. So, during the data preparation, the dataset was divided into three parts, that is training, validation, and testing. The format of data was converted into the format which was required to serve as an input to the Euro models. We trained the deep learning based model, that is the Euro V5 plus attention model, and we evaluated the model using precision required X4. So, some of the training parameters includes the image size of 640 by 640 pixels, batch size of 6, and epochs were 500. The GPU used to train the model was 6 GBs. The quantitatively model was evaluated using precision, recall, and F-score, which are the three indicators in the studies of computer vision. These are the quantitative results. It is observed that the F-score computed by ECA embedded Euro V5 was 0.96, which was higher than Euro V5 plus CBAM model, which was 0.95. The mean average precision for ECA model was 0.98, which was also greater than CBAM model, which is 0.95. The utilized by CBAM model was slightly less than ECA. However, the computational time of CBAM was greater than the V5 ECA model. So these are the visual analysis of the detected landslides. It can be observed that the landslides are detected efficiently by V5 ECO plus V5 CBAM model. The first row represents the model of the results of CBAM model. However, the second represents the results of ULV5 TCA model. So yes, it is observed that deep learning model can provide the enhanced result in the studies of landslides. The recent scientific as well as the technological advancement can be integrated for extracting the landslide related informations. Particularly, the deep learning models are needed to apply for the better understanding of this hazard in the fragile settings like Himalayan region. Yes, the application of landslide detection can be crucial in the development of early predictions model because by detecting the landslides in the from the satellite images, we can map the landslides and we can identify the potential locations which can serve as a critical input towards the development of landslide prediction models. Yes, of course, the landslide detection can also be crucial for landslide susceptibility mapping and in the generation of the landslide inventories. Yes, the accurate landslide detection models can be a valuable addition towards the Sendai framework. So these are the references which were used during this study.
Yes, yes, vision transformers, yes, exactly. They are being utilized extensively. However, what we are planning is at the initial level, we have just implemented the popular attention-based models. So, which are embedded within the YOLO V5 small version. So, yes, in future, yes, we are of course in the preparation of the model, which can include the vision transformers. However, they can be integrated with the attention models as well. So yes, this study is in progress, maybe.
Yeah.
Yes, vision transformers, of course, it's a good idea. It's a good idea. Yes, it can be done.
We'll take some questions on the chat.
Dr. Naveen,
Yes, sir. Yes, sir.
quick question.
Yes,
Since
sir.
you are using YOLO based model, so
Exactly.
YOLO V5, how it will
Yeah.
be better than YOLO V8 currently, which is available?
Yes, yes. That is the recent one.
Yeah, yeah.
Yes, so maybe the attention models, they enhance the accuracy. However, as of now, it will be not be justified to compare the YOLO V8 with the attention embedded V5 because it requires the experiment for comparison of, yes, of course, the V5 and V8. However, V8 is the updated and the modified version of V5 as well only.
Yeah, that's fine. So YOLO V8 would be the best model for
Yeah.
for this landslide detection, right? Which result probably that better than the attention-based YOLO V5, right? Maybe even
Yes,
more
sir.
sets are already incorporated there.
Yes, yes,
Need
yes.
to just check that.
Yes, yeah. I'll keep it in mind that yes, it can be experimented. How well does the YOLO V8 performs, and what is the accuracy that will be produced using V8? Then we can definitely come up with some results, and we can comment.
Okay, fine, fine. Naveen.
Thank.
So,
Where is it?
no, physiography plays an important role in the occurrence of landslides.
Pardon,
What
sir.
physiographic characteristics that you have considered in your deep learning model?
Sir, can you repeat it once more?
Physiography plays a very vital role in detecting the landslide prone zones.
Yes, yes, sir. Yes, sir. Exactly.
What are the characteristics of those physiography of the Himalayan region that you considered in your deep learning model to give your results?
Sir, as of now in this research, we have basically tested, like, given a satellite image. So on the basis of visual interpretation as well as the computational processing with how efficiently we can detect. So it is basically the yes or no predictions only given in any satellite or satellite image. So we haven't considered the attributes and the proxies as well as in this experiment.
So
And,
have you tried historical data and then the corresponding remotely sensed data to validate some of the findings that you have right now?
not with this data set, sir. This was the open source data set of the China. So we have used this one only. So yes, in future we are planning to we are planning to generate the data of Himalayan region, particularly the Himalayan belt. Then probably we will incorporate the other proxies in that study.
Okay, thank you, Naveen.
Thank you very much, Chair and Co-Chair.
Thank you, Naveen.
Yes. Thank you, sir.
So we'll move on to the next paper, that is paper number 3 of 4. The authors are Parasuram Yadav Palla, Amba Shetty, Bobby Raghavendra, and Venkata Narsimadhan Adap.
Good evening, I'm Parasuram from National Institute of Technology, Karnataka, Surat. I work on hyperspectral data analysis, and one of its main applications is mineral classification. This presentation includes my work on a CNN model proposed for mineral classification. Abstract. Hyperspectral imaging is a powerful technique in remote sensing. Hyperspectral images provide detailed spectral information for each pixel image and therefore enables a more comprehensive understanding of the Earth's surface features and the objects it contains. Mineral identification is a challenging task due to subtle differences among the spectral signatures of minerals and limited ground truth for verification. Despite the advancements, no dedicated deep learning expert system exists for mineral classification. Therefore, one-dimensional CNN, a simple one-dimensional CNN model is proposed to test the mineral classification using a virtual sample generation technique that is employed to generate training samples for the proposed model. Overview of this presentation includes related work and proposed 1D CNN model and data considered for the experimentation. Results are discussed and conclusions are presented, followed by the references at the end of the presentation. Related work. Mineral classification is a specific application within HSI analysis, and it remains a challenging task due to subtle differences among mineral signatures and also insufficient ground truth. Segmented upper hull, a normalized cross correlation algorithm, and a spectral curve fitting analysis compare spectral signatures of different targets with respect to the ground truth or reference spectral signatures of minerals in order to identify and detect the different or distinct minerals. Expert systems. Expert systems like SAV classifier, tetracoder, X-ray diffraction, NGO map, MICA were developed for mineral identification. But the performance of these expert systems dependent on training samples. X-height used segmented upper hull diagram to deal with intra-class variations and obtain good accuracy. But its design is very complex due to the number of subclassifiers are equal to the number of total classes present, total mineral classes to be identified. Research gap. So there are many advanced algorithms like machine learning techniques were designed for hyperspectral image classification. There is no deep learning based expert system specifically for mineral classification is available. The objective of this work is to come up with a deep learning based model for mineral classification. A virtual sample generation technique is used to generate more training samples for the deep learning models, which require more training samples. A significant degree of resemblance or similarity can be said to exist among spectral signatures when the value of spectral angle is smaller than 17.2 degrees as per reference step. Therefore, an angle of rotations are chosen to be 12 degrees at max with an interval of 4 degrees to assume maximum similarity. That is 0 degrees, 4 degrees, 8 degrees, 12 degrees. Similarly, minus 4 degrees, minus 8 degrees, minus 12 degrees, one-dimensional vector rotation operation being considered to improve the number of training samples so that deep learning models can be employed in mineral classification with the available training samples. Separate mineral data is used for experimentation on a spectral library of minerals. 5 minerals presented here are showed extracted as a training sample. And this figure shows how spectral signatures are generated using the one-dimensional data rotation operation, that is virtual sample generation method. This figure clearly shows the diagnostic features of each minerals are intact, and at the same time there are different orientations are available for each and every mineral so that intra and interclass variations can be addressed clearly with the deep learning models, which are made for identifying diagnostic features wherever they are present in the data. The confusion matrix for 5 minerals are shown here. Calcite, chloromuscovite are completely identified without any errors using the 1D CM9 model. And at the same time, alunite, buddignite, and kaolinite are identified with the higher accuracy. The performance of proposed mineral classifier is tested with respect to the SAM and X-type classifier. X-type is a ANN classifier, and the table shows that proposed 1D CM9 model achieved higher accuracy than both SAM and X-type. Conclusion: performance of proposed 1D model is compared with the performance of SAM and X-type classifier. Experimental results showed that proposed model outperformed X-type and SAM in classifying all the 5 mineral classes. And automatic training sample extraction techniques for mineral classes present in the hyperspectral data facilitates further exploration of DL-based models in mineral classification. These are some of the references.
Any questions from the audience? Yeah.
What is the size of the test data set?
Test data set contains more than 600 by 500. Mineral samples generally in the hyperspectral data, abundance of minerals is hardly 0.5%. So getting training samples is the difficult. It is not possible. So that is where mineral classification, addressing mineral classification with the deep learning models is what not addressed so far.
Is this an open data set or?
It's a open data set. This is free level.
What's the name of the
Separate data set, and that is available, that is captured over the Nevada region, USA.
I see. I was thinking it
we have considered also like with more traditional deep learning this determination, like you see, could have used. We have our like you have a bit, could have used only GAN also, right?
Yeah.
So instead of like, I mean, the current method that you're using, that's also quite
Virtual
interesting.
generation.
But you could like instead GAN or something, or even additional of encoder, and then you could have sample from the latent space of the additional of encoder, right?
Yeah.
To generate more data. So did you try?
Yeah, I tried that, but I haven't get good results. But that was because of lack of time. I could not do it. Actually, we could do it.
Thanks.
But this is the more that 17.2 degrees is the what maximum resemblance between what pure samples of the minerals. So this is the simple model which I could do it in a short time. So I did it. But actually, we can do it GANs also.
Yeah, I mean, your idea is
GANs
quite interesting in the sense it comes from more from the domain, right?
Yeah.
Rather than like some
other,
kind of deep learning ideas.
Yes, whatever training samples are available, we can take up to 17.2 degrees, maximum resemblance even 0.1 degree, 0.2 degree, 1 degree. So like that, we can increase number of samples without any, having any randomness in taking.
This can be combined, kind of.
Yes.
More deep learning, this augmentation, and this can be combined.
Yes, so that is the main idea to implement the basic concept.
Anybody else? Quick questions.
Yes.
What 1D CNN model you have used?
1D CNN model of three hidden layers and one output layer, sir. And since these are all spectral vectors, so
No. How many convolution layers have you used?
three convolution layers. Three convolution layers with ReLU activation function.
Total, what is the weight layer total?
Sir?
Total number of weighted layers in the model, weight layer?
Weight layers of filters I used 5.
No. Three convolution layers.
Yes, sir.
Right. There could be used some dense layer, right?
Dense layer at the output
So
with the softmax function.
okay. Right. Did you experiment a little bit for doing little more deeper model?
Yeah, I experimented with more deeper models, sir, but the diagnostic features are available at small wavelengths. So that will depend upon the what bandwidth.
What is that one? But here is not. Okay, fine.
Yeah, so those bandwidth depending upon the bandwidth of the sensor. So there is a range of frequencies at which diagnostic features to identify the different.
1D kernel size, what you have selected?
1D kernel size 975.
Okay.
975 I had varied, and 9 gave good results. I did not put much results here in a brief.
Thank you.
Thank you. We'll move to the next paper. So that's paper 149. Authors are Diksha Agarwal, Uttam Kumar, and Rikhil Gupta. The title is Comparative Analysis of Unsupervised Pre-training Models for LULC Classification with Limited Labeled Data.
Your presentation is there?
We might have received.
Okay. Next is next paper you can take. 55.
Okay. 55 is authors are Sudeepan Saha and Naimish P. Machchar. Title is Enhancing Confidence of Unsupervised Change Detection in Hyperspectral Images.
Meanwhile, you can give
Right, presenting our work on enhancing confidence of unsupervised change detection in hyperspectral images. I am Sudeepan Saha, a faculty member at IIT Delhi. In this work, my co-author is Naimish P. Machchar. Work is about change detection, which is one of the most popular tasks in Earth observation. Change detection involves analysis of bitemporal images, that is, the pre-change and the post-change image. Change detection often serves as the first step towards time series analysis, and multi-temporal analysis. This work is specifically focused on change detection in hyperspectral sensors. Hyperspectral sensors are popular in Earth observation due to their ability to capture and analyze detailed spectral information. Unlike traditional multispectral sensors that capture information in a few broad spectral bands, hyperspectral sensors are capable of collecting information in hundreds of narrow spectral bands. The fine-grained spectral information allows hyperspectral sensors to capture unique spectral signature of objects, which is useful in several applications. For example, vegetation mapping or mineral characterization or water quality monitoring, and also, of course, in the urban applications. Can be supervised and unsupervised. This work particularly focuses on unsupervised change detection. Deep learning based unsupervised change detection methods use transfer learning. They are dependent on the availability of a suitable feature extractor. However, availability of such feature extractor may not be straightforward in the case of hyperspectral sensors. This is because the networks between the multispectral images cannot be reused from hyperspectral images. Furthermore, even if we have a filtered model for one of the hyperspectral sensor, as we can see in the table in the right side of this slide, this cannot be adapted trivially for another hyperspectral sensor due to the large variation in the band configuration among different hyperspectral sensors. To get this issue, a previous work proposed the use of untrained model as bitemporal feature extractor for change detection hyperspectral images. The advantage of using untrained model is that it can be initialized to ingest as many input band as we desire. Furthermore, it can be initialized to as many layers as we desire. Why we can use untrained model is that in this case, we are not trying to obtain specific output labels for the images, rather we are just using these networks as bitemporal feature extractor. One of the aspects of using such untrained model as bitemporal feature extractor is that slight perturbation in the weight of the untrained model can produce different change detection results. This is both a challenge and an opportunity. How? We come to the next slides. Way to look at the slight variations in the network weights is from the perspective of modeling uncertainty. Predictions from different outputs by using the different perturbation of the weights can be combined, form an ensemble. By using this idea, we use change detection maps and we use their pixel-wise deviation to obtain the uncertainty map, that is a pixel with strong variation in the row, that is bit change magnitude values, can be considered as a pixel for which the prediction is not confident or more uncertain. Whereas if the variation is less, then you can say that the prediction is more certain. We show the result of the Santa Barbara scene. Here we can see the pre-change and the post-change images. You can see the reference map and the result obtained by the proposed method, where our white shows the unchanged pixels, black shows the changed pixels, and the gray we see either the pixels for which the reference label is not known or the pixels for which our method is not certain, is not confident. You can also see quantitative result. We clearly see that the proposed approach improves the result over the confident pixels. Our work, we proposed a way to use variance as a way to identify confident pixels. In future, we would like to compute confidence from a single output instead of ensemble of outputs. Thank you.
No, we can take the questions from chat. Oh, yeah, there's one.
What is the model you have used? So this is a very simple model. I don't remember the exact architecture, but this is not any like, I mean, any definite like architecture. This is just a simple model which uses like about 3 or 4 convolutions. So the main idea, I mean, let me give a bit of background. This work, of course, we are proposing in the context of hyperspectral images, is also because use of the like one of our previous work, we showed that for hyperspectral image change detection, we can just use an untrained model, because getting a trained feature extractor is not always trivial in the case of hyperspectral images, right? And then once you are using untrained model, untrained feature extractor. So when you're using a trained feature extractor, of course, you have just one model, right? But when you're using an untrained model, you can always slightly perturb the weights and you can get as many perturbation of the weights as you want, right? And then you can compute a kind of variance among these results. But then, of course, this result can also be applied to multispectral or SAR, any other change detection also, with a bit of caveat that they are getting this different perturbed versions is not straightforward. So we also applied, so this is not in this paper, but we also applied this same idea to the multispectral SAR images. And then we found a bit better method. So right now there is another paper which is under review, where this method that we are presenting here works as a kind of comparison. And there is another better method which hopefully gets accepted, and then we will come to know which serves as the main method.
Okay, I'll take a few questions later on. Yeah,
Sure.
Short of time, right? Okay.
One small question. Somebody asked.
Yes.
Experimental results and any other change detection.
So not only on this scene, so this the link that I showed that comes with 3 different hyperspectral scenes. So we did on this 3 obviously hyperspectral. Yeah. And then we have also experimented on the same idea in also on the spectral and the SAR images, but which we have submitted as another paper. But they are like, this is only a method compared, it's not the main method.
Okay. Okay, fine. We can take question after this, right? Okay, next. Next, please, Samrat.
We'll move to the paper. Yeah.
I will be presenting a paper on analysis of unsupervised training and supervised learning models with limited label data for LULC classification. This paper is co-authored by Professor Uttam Kumar and Ritu Gupta. For the introduction, I would like to brief you about hyperspectral imaging, which is concerned with the extraction of meaningful information based on radiance acquired by the sensor without substantial contact with the object of interest. Land use refers to the intended purpose of the land encompassing man-made activities like agriculture, construction, etc. Whereas land cover denotes the natural ground surface characteristics such as forest, water bodies, bare soil. Accurate classification of land use and land cover LULC categories from hyperspectral imaging remains a pivotal task in remote sensing and geospatial analysis due to its varied real-world application. There are certain challenges which are there in accurate LULC classification, and in this study, we are concerned with the below three challenges. First one is the availability of label data. So as we know that labeling HSI requires per pixel annotation, which tends to be time consuming and expensive task, and also it requires involvement of domains for it. Secondly, the high dimensionality of this HSI data, which comes in the form of high spectral bands and spatial resolution, which tends to give a slow convergence of models, that is machine learning models or deep learning models. Thirdly, there is a limitation of limited label data availability. So as we know that it requires it is a very time-consuming task to label HSI pixel. There are often cases where limited label data is present, and which tends to lead the deep learning models to often fail to generalize well and overfitting. So to address these challenges, this study thoroughly examines critical issues by comparing 6 combined generated pre-training discriminated fine-tuning models with 2 standalone discriminated models. The primary goal of this study is to provide a comprehensive comparative analysis while evaluating the effectiveness and robustness of unsupervised generated pre-training models in limited label data conditions. In this study, we evaluated 3 real-world and publicly available hyperspectral datasets, namely Cambridge University, Geoscience, and Pilinja, with the proposed methods. These datasets encompass various environmental settings in high spectral band definition. For the evaluation metric, we have used a card score, also known as intersection of union, and Cohen's kappa metric. Methodology, so I would like to brief you about 3 different kinds of deep learning models, machine learning and deep learning models, which we are using in this study. So first one is discriminated model. So in discriminated model, the general idea is to estimate the parameters of probability of the Y, which is the label, and given X, which is the input data set, with the help of training data. It learns the boundaries between classes in a data set and are robust to outliers, but they are not able to generate new data points. Whereas in generative learning, a generative model, they distinguish between the classes based on the distributed probability, and they estimate the prior probability P of Y and likelihood probability P of X given Y with the help of training data and using Bayes' theorem. So these type of models are not robust to outliers, but can tackle a more complex tasks. And also major advantages, they are capable of generating new data points. The third type of model is a combination of the distributed and generative learning. So this combined model is trained in a 2-branch setup. The first branch consists of generative model, which utilizes the unlabeled data and label data for latent feature extraction using generative learning. And then once we get this embeddings, we fetch the embedding into the discriminative model as a classifier and use the available data to fine-tune the discriminative model and do the predictions. So in the given figure, the experimental pipeline is shown, which includes the integration of dotted dot line, symbolizing the combined generative discriminative model, and its exclusion representing the standalone discriminative model. So here we have a HSI cube, which is tracking along the spectral dimension, which is then normalized using a bandwidth max normalization technique and then fed into the neural network. For the experimental results and discussion, the predictive performance in the presence of limited label data is done. And as we have used 6 combined models, which are PCA, SVM, PCA, random forest, autoencoders, SVM, autoencoders, random forest, SCAR, SVM, SCAR, pilot. The SCAR is self-supervised contrastive learning. And 2 standalone distributed models, which are SVM and random forest. So here we see that, so this table, we see that the comparison of test accuracy drop with limited label data is shown as compared to when 100% of label data is available. So here we, the highlight is that there is a very less drop in accuracy performance in the combined model setup as compared to the standalone model setup. Secondly, we also assess the predictive performance in the presence of label noise. So this is done when there is a availability of 100% label data, but 30% of the label data is subjected to some noise or corruption. So here we see that the discriminative models such as random forest and SVM outperform other generative discriminative models. This observation suggests that the standalone discriminative models were able to capture discriminative features even when the inputs were corrected. In the conclusion, this study systematically compared generative and discriminative models for land use land cover classification under constant label availability. It explores scenarios with full and limited label data scenario, limited label data, also considering label corruption. The results indicated that generative pre-training aided in preserving performance under limited label data conditions with SCAR, autoencoders, PCA models showed notable resilience. Yeah, raw random forests and SVM performed well under label noise, implying their robustness to corrupted labels. The findings have implications for researchers working in LULC classification, offering a perspective on model selection and design to optimize accuracy in real-world scenarios. Thank you.
Anyone have a quick question? Okay, lecture, right? So just can you go quickly that the table was there, right?
Yes, sir.
Which are SVM.
So I just my suggestion take it, right?
Yes.
This data is the most popular data set,
Yes.
right? So a lot of more researchers have done in the deep learning field, and those results, if you compare it, that would be the better, because whatever the method you are reporting is none of the deep learning based model, and the result would be even much better there.
Sir, actually, these are the accuracy drops. So if
These are the accuracy drop. Where is it that accuracy table
the accuracy table is shown here.
with the
So if it is performed with the 100% of label data, if it is performing 90%, and with the 30% label data, it is performing 88%. So the drop is shown as 2%. So that table is referring only the drop. that is 2%. But here we are showing the actual accuracies in the present of 100% label data, but 30% is corrupted. So we are seeing that it is almost like 80% or like higher accuracy. It's not.
Okay, if it is like 0% label noise, what would be the result?
So results are I have not noted in the paper, but they are 80 to 85% accurate.
But present study says that if you look at the old papers,
yes,
they are getting the even close to 98, 99, even the class-wise average, and even that result is too promising.
Yes, sir. Sir, I'll like I should add the
yeah,
results.
because you just looked it right, that would be nice.
Yes, sir.
Because these are the so standard results.
Yes, sir.
Right?
I should have write the 100%.
Yeah, we do also, our team worked in long while 2 years back.
Okay.
Good.
Thank you.
It's interesting, right? And with them more. Fine. Thank you.
Okay. Generative models, which generative model you have usually used?
In this, I have used autoencoder, PC8, and one more SCARS, which is self-supervised contrast learning model.
Not exactly probability related, fourth areas probability. Not you know, right?
Like autoencoders are like generative models which are based on the theorem of how it generates the data. So using Bayes' theorem only. Like it only takes into account the input, which is X, and not the labels, which is Y.
Okay, thank you.
Thank you.
Next paper is paper number 316. The authors are Samrat B, Nitish Reddy Banda, Akhil Galla, and Dr. Arun PV. The title is Navigating Noise in Chandrayaan-2's IIRS Hyperspectral Data, Advancing Quality via Deep Learning and Shear Loss.
Hello everyone, my name is Prakash and I am excited to share insights from my paper titled Navigating Noises in Chandrayaan-2 IIRS Hyperspectral Data, Advancing Quality via Deep Learning and Shear Loss. So, my co-authors are Nitish Reddy Banda, Akhil Galla, and Arun PV. We are from IIIT CCC. Our research aims to tackle noise challenges in hyperspectral images from the Chandrayaan-2 IIRS dataset. Using a convolutional neural network with Steen's unbiased risk estimator loss function, we are innovatively addressing these issues. This approach promises to enhance image quality and open new avenues for scientific insight. Today we are talking about hyperspectral imaging is like a superpower for pictures. It helps us to find out what things are made of by looking at different colors. We use this in many areas like farming, watching an animal, and finding minerals, and even exploring the moon. In our rural images from Chandrayaan to noises challenges surface during IIRS data collection. These include mixed pixels, triple noise, Gaussian noise, and Poisson noise. Clearing these noises is vital for precise lunar data analysis. To sum up, missing pixels is due to sensor errors causing gaps. Triple noise is due to atmospheric conditions creating unwanted patterns, and Gaussian noise is due to electronic fluctuations causing random variation. Pressure noise is because of photon detection changes impacting the brightness. Now let's explore our noise reduction methodology. Data representation. In hyperspectral imaging, our image Y has spatial dimension M cross B, capturing across different wavelengths, and where M and N represents spatial dimension and B is the band count. Denoising objective. Our goal is to purify the image X from the observed mix Y equal to X plus W. Here W is the noise and Y is the raw HSI, and we are trying to generate X the denoised image from raw hyperspectral image and CNN-based inversion. We use a convolutional neural network with streams under risk estimator, tune up the noisy image file and get an estimated length. Estuary loss is a budgeting tool for the noise. It has two sides. Reconstruction error (MNC) rates our accuracy in creating the clean images, and other term is other term finds the divergence present in an image. So our refined estuary loss combines this fine-tuning denoising by evaluating MNC and measuring divergence. It ensures accurate reconstruction and effective denoising with each iteration. Our denoise model effectiveness was rigorously tested on 4 hyperspectral datasets, CU, Cupid, M3, and IIRS data. We ensured uniformity through rigorous pre-processing, including normalization. And this table presents the peak signal to noise ratio PSNR and signal to noise ratio SNR values for various data sets, including both the noisy data and the corresponding noise data using actuary-based CNN. And this is with added Gaussian noise. And to stress test our model, we intentionally added Gaussian and Poisson noise systematically, evaluating its robustness under diverse noise conditions. Now let's dive into the results and insights gained from these extensive experiments. Train our CNN on noisy datasets for hyperspectral image denoising and estuary loss function refine our model iteratively, effectively removing noises while preserving spectral details. Testing and validation. Model performed exceptionally on raw noise-free data, showcasing noise reductions and feature preservation. Integrating estuary loss into CNN significantly enhanced image quality and reduced noise across diverse datasets. Exceptional performance on Cupid, M3, and IIRS datasets assessed by DSNR and SNR methods. M3, notably, CMOS M3 image showed negative values in both Gaussian and Poisson noise simulation. This is an interesting area for future exploration. In summary, our approaches excels in hyperspectral denoising with promising results across different data sets. These are my reference papers.
Any questions from audience or you, audience?
Am I audible, sir?
Yeah, you can ask the question.
May I ask one question?
Yeah, go ahead.
Yeah, in IIRS data, what is the wavelength they used? Like IIRS data is having 0.8 to 5 micrometers. So how much wavelength they have used for the denoising?
I didn't get your question, but I don't remember the exact wavelength range for IIRS dataset, but I have used the dataset which is publicly found with level 3 pre-processing from ISRO website.
No, it is given up to 5 micro, like thermal range also there, na 3 to 5 micrometer, and 0.8 to 2.5 micrometer means this as SWIR region. So which range you have used in your analysis?
I think it's a first one, but I can check that and I'll let you know.
And what is this method is applicable for other range also, like other thermal range?
Yes, it should work because I have tested it on 4 different data sets.
But there we have to do thermal correction, some thermal noise correction. So different approach we have to use, but because this approach may not work I think you have to check properly.
Yeah, we have developed this for especially for IRS dataset. So we can extend this for other datasets also, but we need to check with the data.
Okay, thank you.
Okay, so you have not reported any visual result, right?
Yes, sir.
Because since you are doing denoising, cannot be rely only on the looking the numeric values. Until let's see that the how that denoisy data that is looks, I mean the with the ground truth and all the things. Comparison should be there.
In the paper, I have added the images, sir. Due to time constraint, I have removed some things in the presentation.
Oh, okay, fine, but that's fine. Maybe the slide would be better to make them right. Yes, fine. Sir, you have any? Okay, thank you.
Thank you.
Thank you. That concludes our session today for deep learning. Thank you to both the chair and all the participants and presenters.
Thank you.
We'll close the session, and I would request everyone to move to Amantran now, where we'll be having a cultural event.